Hello everyone, I welcome you all to the second lecture of our data science project for predicting the lipophilicity of organic molecules using graph neural networks. So in the last video we did some data analysis and we truncated the data set and we got rid of molecules having molecular weight greater than 700, and we were left with this df underscore final data set with 4192 molecules. So we are going to be taking ahead this final data set for generating graphs from smiles notations. So of course in this video we are gonna be talking about how we can generate graphs from smiles. So I had saved this data set containing 4192 molecules in a CSV file called lipophilicity underscore final here. So what I'm gonna do is I'm gonna load it again here, and let's just have a quick look at our data set. So this is the data set with Campbell IDs, experimental lipophilicity values, and smiles notations. So let us just say we want to generate the graphs for a single smiles string. So what I have done here is just grabbed a random molecule. You can just take any molecule. So at index position 92. So let's see the smile for this. So this is the smile notation for the molecule at index position 92, and let's visualize this molecule with the help of rdkit star.mold to image method. So this is the molecule at index position 92, and let's just say we want to generate graphs for this particular molecule. Now there are various ways you can generate graphs. You can generate custom graphs on your own using rdkit or using Networkx. But in this tutorial I'm going to be introducing you to a pre-made method of Pytorch geometric for generating graphs from smiles. So I'm taking you to the official documentation of Pytorch geometric, and in here if you on the left hand side, if you scroll down to the package reference and if you go to utils section, and in here if you search from smiles, in here you can see we have a method from smiles which converts a smile strings to a torch geometric data instance. So let's click on this. In here you can get information about this method. So we are going to be using this method from underscore smiles for generating graphs, and it takes in argument as smile strings. You can also put in hydrogen if you want. So with underscore hydrogen you can do true if you want, calculize if you want. So yeah, so it will basically furnish the graphs representation of molecules, and in here that's what I'm doing here. So I'm using this from smiles method of Pytorch geometric, and I'm just putting in the smile string of this molecule, and we can just not include hydrogens. So let's run this, and you can see here this is the graphical representation of the molecule here. It has X, edge index, edge attribute, and smiles notation. And if you look at the type, so this is belongs to torch geometric data instance, and this is a homogeneous graph. And as you can see here, there is a lot of information. You can see the number of nodes and all that thing, and I'm gonna be talking about that in a minute. So now what is X? X is basically the node feature matrix. So if you g.x, so if you remember from our last lecture, we had node feature matrix, and these columns represents the node attributes or node features, and these rows represents the nodes or atoms in a molecule. So if you want to know the number of atoms or number of nodes, we can just use g.num underscore nodes attribute. So there are 27 atoms or nodes in this molecule. And number of node features, if you want to see, you can just use num node feature attribute, and there are 9 node features or node properties that the from smiles method has utilized. And what are these node features? We will see that in a minute. So okay, so X is a node feature matrix with a size 27 into 9, where 27 is the number of atoms or number of nodes, and 9 is the number of properties or number of attributes or features. uh, Edge index is basically, if you click on this, uh, edge index is basically graph connectivity in COO format with shape 2 into number of edges, and number of edges is basically number of bonds. And how many number of bonds are there? There are 60. There are basically 30 bonds, and we kind of double that, because both the atoms are making the bond, so we double it. So basically we have 30 into 2 number of edges. And if you wanna have a look at that, if you wanna expand that, all you need to do is just use edge index attribute. So this is the edge index in COO format. And again, if you want to see the edge attributes, that's basically we have 3 edge attributes, and edge attributes is basically on left hand side here, on the number of rows represents the number of edges, or twice the number of edges. So 60 would be the size here, and here the number of columns are 3, or edge properties. So what are node attributes and edge attributes that we can see in here? If we go back, if you can see we have a source link here. So if you click on here, you can see, so if you remember, we had 9 node features or node attributes or properties of the atoms, and these are the properties: atomic number, chirality, degree, formal charge. And if you count 1 2 3 4 5 6 7 8 and 9, so these are the 9 properties that from smiles method is utilizing. Again, this is a pre-built method of Pytorch geometric. You can include more features or properties if you want. For that you need to custom generate the dataset, and in my future videos, if I get a chance, I'll definitely talk about that. But these are just few, and there are plenty of atom properties out there on RDKit that you can utilize and include in your node features. And regarding edge attributes, again, if you remember, there were just 3, and these are the 3 properties that from smiles method has included: bond type, stereochemistry, and is conjugated or not. So if it's conjugated, it would be 1. If it's not conjugated, it would be 0. So yeah, going back to our Google Colab notebook, the next I want to talk about is the Networkx library. So Networkx is used for network analysis in Python. As you can see here, Networkx is a Python package for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. And if you go to this documentation here on the tutorial section, you can basically use Networkx for generating graphs as well. And again, hopefully if I get time, I will talk about how you can use Networkx for generating graphs. So what you can do is first generate an empty graph, and then add nodes and edge attributes in here. But since we already have a graph, we don't really need to generate right now, but we can use this Networkx for analyzing our graph. For example, in here, first what we need to do is, since this is a torch geometric data, we need to convert this graph G into Networkx graph, and that you can do using to_networkx method of Pytorch geometric. So in up here, As you can see, I have imported two Networkx method from torchmetric.utils, and that's what gonna be we're gonna be using to convert our torch geometric data to Networkx graph. And let's go ahead and do that. So G is now, if we look at the type, G is a Networkx class. And if you want to see the number of nodes, again, how many number of nodes we had in here, around I think, if I remember correctly, 27. So let's check again. Yeah, so we have 27 the number of nodes or number of atoms. And if you want to see the nodes, it will give you the labeling of all these nodes here. And the number of edges, we had 60, 13 to 260. So yes, we have 60 edges, and you can also list the edges here. Yeah, so now another interesting thing you can do with Networkx is you can draw the graph. Basically, let me print out the molecular structure again here. So this is the molecule that we are working on right now. And in terms of graph representation, you can draw this with the help of Networkx using draw method. All you need to put in Networkx class G and with labels true. So this is the basically drawing for this molecule here. As you can see here, this is the 5-member ring here. This is the 6-membered aromatic ring here, and this is the 7-membered ring over here. And this is again the benzene ring, and this is nitrogen, this is methyl and methyl. So and this is carbon, and this is carbonyl. So this way you can represent your graphical data as well. And if you want, you can also save this. And it will be saved in here, and you can just use this in wherever you want. So yeah, that was all about generating graph for one molecule. Now we have a whole data set with more than 4,000 molecules. So if we want to generate the graphs for all these molecules, what can we do? So next section here is for generating graphs for the whole data set. So this is the data set that we have. This is really simple. All we need to do is run a for loop. So basically we will enumerate over our smiles that will provide us index as well as the smile strings, and using from smiles method we will generate the graph. Next, what I am doing here is I am converting the node feature matrix values to float. If we go above here, this G dot X dot D type is, it's an integer, and what I have seen is while model training it causes problem, and so it's better to convert these integers into float values. So that's what I'm doing over here, converting our node feature matrix to float values. So next what we have is we also need to include our target. And why would be our target? And I'm converting into tensor, and it will just pick up the y values from the index position of the smile. So and again we want it to be float values, and in the and over here I am just appending these target y values to our graph, and in the end we are kind of appending this whole graph to the empty graph list over here, so that at the end we have graphical representation of 4,192 molecules in the form of a list. So let's run this. So yeah, let's see the list type. So this is again torch geometric data, and it's iterable since it's a list. Now it would give us the same type of structure. For example, this data has X, which is node feature matrix, edge index, edge attributes. This is the smiles notation, and in here we have also included our target. And again, if you want to expand, you just use .x for node feature matrix, and now you can see here these are floating values. And if you want to see Y, this is the Y for the molecule at index position 1. So yeah, this was one way. Another thing is that I want to talk about is in-memory dataset. So what happens is, let's say you have a large number of molecules, maybe around 10,000 or 20,000 or 100,000. So every time you run the code, you don't want to generate your graph data again and again and again, right? So what you want to do is you want to save your graphical data on your CPU. Now what I have done here is, so if you go to creating graph dataset section of Pytorch geometric, you will get information about how you can generate in-memory datasets. Basically it has provided information here. We provide two abstract classes for dataset. First one is torch geometric dataset, and another one is in-memory dataset. So I have already talked about how you can generate this class, and now we are going to be talking about how you can generate this class of dataset, and which you can store on your CPU. And what I have done here is just copy and pasted this whole section, and there's information in here about what these functions are. You can use transform method. This function dynamically transforms the data object before accessing. We have pre-transform function that applies the transformation before saving the data to disk. There is a pre-filter function, so you can read about this, but I will provide you just kind of the overview of how you can generate in-memory dataset. So just copy paste this, and I have pasted it over here. And in the process section, all I have done is just copy pasted this part where we have generated the list of graphs, right? So that's over here, and that's pretty much it. In the end, we have a data list which is equal to graph list. So I have not really made any other changes over here. And yeah, we want the data to store as a .dt file, so you can use as data as well, whatever name you want to give. And what would happen is when we run this, in the next line of code, we are gonna be creating an instance of this class, my own dataset. And what would happen is we have to put in the address where we want to store this graph dataset. So I just want to store in here in the temporary folder. If you're running it on your computer, you can provide the path for that folder, or wherever location you want to save that data. So what would happen is that when I run this, it will process, and once processing is done, we will see processed and raw folders, and our data is in here in the data.dt file. And what would happen is when we rerun it again, let's say I rerun this again, it would check if the processed and raw folders are there, and if it has data.dt file, and if the data is found, it would skip generating the graphical data again. So basically it will use this data and store it in a lipo or whatever variable name you have given, so that you don't have to generate your graphical data again and again. And again, this is a temporary folder of Google Colab. So once we are done with this, it will just disappear. But in case you are using it on your own computer, make sure you are using the same path, and then you are all good to go. You don't really need to generate your data again and again. So I think this is really good feature, and highly recommend you to go this path. Again, if you want to look at the type, this is belongs to a class of my own dataset, which is in-memory dataset, and it has the same kind of representation. So any random molecule we have taken, it has x edge index, edge attributes, miles, and of course y. So if you want to see the what x is for any molecule, let's say just 23, it will provide you the node feature matrix, and y would provide you the target value. Okay, so the length of our data set is 4192. So yeah, that was all for today's video. In the next video, I'm gonna be talking about splitting our data set into training and test set, and then defining our models and how we can define our training and evaluation functions for training our data. So stay tuned for future videos. Thank you for watching.